but we've not seen exactly why we are using an onion, or why we chose this construction of an onion, and how this construction of an onion actually looks like. So my goal right now is to basically walk you through the iterations that onion routing packets have done so far, and why we chose this construction we have here. So just to be funny, I have once again the difference between distance vector routing, which is IP-based routing basically, where we just have the recipient's address, and source-based routing, where we have a list of intermediates through which we can then finally reach our destination. And we've been talking about this before during the trampoline talk, about why we chose source-based routing in the first place, and what the disadvantages and advantages of each other are. So obviously here we just we have this list of hops that we'd like to go through. And for the remainder of the talk, I will basically represent this as a list of individual hops that will be attached to our HTLCs and will be forwarded. So this is basically the onion as it looks for user A, and user A receives this list of addresses, or list of hops, and A sees that, okay, the next hop is B. So B comes along and sees, oh, the next hop is C. C comes along, sees, okay, D is the next one, and E, and once E gets it, we have this. This is a terminal node. No need to forward it anymore. So this is all clear text currently, and I guess everybody sees the downsides of this, namely that we know almost the sender, but we know the first peer of the sender, and any node in the list definitely sees who the recipient is. So we can do one better and basically say we, instead of having this fixed list of addresses, we now go and just chop off the beginning every time we process it, and that turns out to be, okay, A sees this thing, sees, okay, I'm supposed to send to B, and we chop off B, now send it to B. B sees, oh, the next one is C. I'll chop off C and send it forward to C. C sees D, and so on and so forth. And so the point here is basically that we now have, while we are routing, each node sort of elaborates or processes this addressing packet, and the packet that is going to be forwarded to the next hop doesn't look like, or has less information than the one we had before. And of course, then E gets it, and E sees, oh, I'm the intended recipient. I shouldn't forward it anymore. Now, this still has this downside of, well, B still sees the exact route and the amounts and who the destination is, but at least E doesn't see who the sender is anymore, or any hop doesn't see who the later one is. But I will get to that later. So, of course, this all being clear text is kind of dumb. So let's maybe start encrypting stuff. So I have chosen this wonderful black color to represent encryption. And so what we have again is that I, as A, receive this blob of information, and I will process it somehow. And from processing this, I will receive the blob that I should forward to the next node. So that stays the same, but now processing actually involves me having to decrypt this blob. So I get this encrypted blob of information. I do some magic, ECDH basically. We'll see how that is transferred actually later. And so I generate a secret, and I peel off one layer of this onion, basically I decrypt the entirety of this thing. And now I see that I'm supposed to forward it to B. Notice that the color got a bit lighter because I peeled one layer off the entire thing. Anybody want to guess why I'm not just decrypting this part, but I'm decrypting the entirety of this? Right, but I could also, if all I care about is my part and then want to send it forward, I could just have encrypted this part and have left the remainder like singly encrypted.
Then if C, for example, which we don't see it, intercepts it before, he could decrypt it before B. Like everything should be encrypted with B's key, and then B should decrypt all of it, and only then should C be able to decrypt.
So you mean like
otherwise, the last person can know from the start where it got from. If he can decrypt the package at the original hop,
C can only decrypt its own hop. That's not the real reason. The reason is
you may want to give multi-ops to the ops. Multi buckets of data to the op.
Well, I mean, I could decrypt the first 2 bytes, and that tells me how many bytes to decrypt. That's also not the exact reason.
Is it to keep the size of the final package unknown?
We'll get to that later, but the real reason, tampering, sort of. The real reason is that if I were just to decrypt this part and keep the tail constant, a passive observer could associate the previous onion with a follow-up onion. So by actually decrypting the entirety of this thing, now this part looks also completely different from what I got on the inside. So I can't really associate the two. There's other tricks we can associate them a bit, but the idea is basically to have the incoming onion and the processed onion as detached and looking as different as possible on every single hop. Okay, so the process is again the same. A gets this packet, has just decrypted it, can now read B, and now it can read the information it's supposed to read and supposed to act on, basically forward to B. Now it chops off its part and it forwards to B. B again decrypts the entirety of the packet, chops off, forwards, and we basically have the same thing again. And we end up at E and T. And notice that at no point the color of this of the onion was the same as it was incoming, right? So at any hop in this process, we change the entire look of the packet, and you can't really associate them anymore. So somebody mentioned it already. We still have a pretty good idea on how many hops there are here, right? It's 3 because at every time we chop off the initial part, and so we know that we are probably getting close, and in particular D knows that E is the final destination because there's just one more hop, which is basically there to signal, hey, you are the destination. So we are still leaking information. And of course, the solution to that is to make a constant onion. Any ideas how we want to create a constant onion?
Put some random data in there.
Is random really good?
Just add it with zeros after the determination. So like E gets the thing that says
Mhm.
terminate, and then everything else you can throw away.
When do you add it? Before or after decrypting? Okay. And so then by decrypting it, by using the decryption stream, you encrypt the 0 pad at the end, right? So, and indeed what we do is we get again this fully encrypted blob of information. A gets this, and we now start processing, and we do that by appending a 0 pad at the end, which is equivalent or bigger than the part that we are going to process on our side, right? And we then decrypt it. And the way we decrypt it is basically an XOR between a pseudo-random stream of data that is starting here and goes beyond the end of the original packet, which was here. And by decrypting this packet, the head of the packet, we also encrypt the trailer of that we just added, the pad. No, it's actually this black that we stripped, and so we add that black here.
And I thought black, like dark black, means it's encrypted several times.
Sort of, yes.
Because the next time you...
Yeah, no, I thought about it, and I wanted to make it clear that the decryption and encryption is basically the same operation. That's why I chose the same color. And once we have that, we can actually chop off the head, and this is the new packet that we can forward to the next hop in our route. And if you were to shift this to the left, we would actually have the same identical size again of the initial packet. And this way, we can ensure that at least from simply by looking at the packet, you cannot infer what position in the route you are and how close you are to the destination. That also means that we have to have basically a global parameter that tells us how many hops to pad to. In this case, we have 4 hops, and we're limited to 4 hops because we could distinguish 5-hop onions from a 4-hop onion. And simply having this information about how far apart the source and the destination are would give away quite a lot of information. What we do in Lightning is we have 20 hops in total. Each hop has 65 bytes. And so when we create an onion, we may fill the first 3, 4, up to 8 currently hops, and then we just pad with all zeros. And whenever we decrypt, we actually generate a stream that is 1,365 bytes, basically because we append one additional hop at the end, which is going to be then shifted in with the rest of the packet. Okay. Yes?
What happens if one of the hops failed to decrypt? Does it return an error? What exactly happens?
That's an excellent question. It also ties in perfectly with the next question I had. What happens if A basically goes here and fiddles a few bits here? So we need some mechanism of detecting tampering, right? And how do we usually protect against tampering? HMACS, exactly, or MACS. What we need to do here is introduce a MAC that ensures integrity of the onion packet itself before decrypting the onion packet, right? So which range of this packet? Let's go here. Which range of this packet should we HMAC? Should we just MAC this part that we are about to decrypt, or should we HMAC the entirety of the packet? The whole thing, exactly. Because if somebody if A was to tamper with something back here, A could basically probe for who is the final destination. Because remember, we have trailing padding in here that is basically just zeros that we only have there because we want to have this constant size. And so if we tamper with something beyond the last hop, and we were only to MAC the individual packets, then this would still work, and we could basically probe out which of these sets we need to tamper, and then figure out which node is the final node in the route. So our HMACs always cover the entirety of the packet, and we'll see this later when I talk about how we serialize the onion. But what we do is basically when A decrypts this, this does not only contain the address of B, but also the HMAC and some additional information that we should give to B. So when in clear text, by the way. So when B then gets the HMAC and this onion, it knows it can verify integrity of the package it just received before decrypting it. And if the HMAC does not verify, then we will just say, hey, go away, it just failed. Tear down the entire route. We can't go on. Yes?
I'm sorry, I keep asking the same thing, but what exactly do you do? What do you mean go away? What happens? What's the protocol exactly do when it fails decrypt?
Mm-hmm. So what we do then is we don't fail decrypting, but we fail verifying integrity. It's the same basically. So the protocol is we send an update at the HTLC. The update at the HTLC contains both the HTLC information as well as the onion. This onion gets stashed away. The HTLC gets added to our commitment transaction, and once we have exchanged the commitment signatures, only then we go back and look at the onion. Right? So we have now committed to an HTLC that is incoming, for which we have an onion. We go look at the HTLC. We go look at the onion, try to decrypt it, maybe fail. If we fail, we say, "Hey, update fail HTLC," and we give it an error code that indicates that the onion failed to decrypt.
You don't say what exactly failed, right?
We don't say what failed, because all we can say is this doesn't match the HMAC I was expecting. So.
Yeah, it's best not even to say that. That's what I'm trying to understand.
I mean that
you shouldn't even tell if it was the HMAC or just failed decrypting.
Well, there is no difference between the two.
You can fail. You can. The HMAC can succeed, and you can fail decrypting. Like
so what can happen is that we fail to parse the payload. That's true.
Yeah.
We currently distinguish those because we find it easier to debug with more information. But you're right. We should eventually just say, well, go away without further details.
Because then you can use a timing attack to try and hack the HMAC.
Yes. Well, timing in this kind of network is kind of hard because we need to be committed first. So we have a whole it's not just I receive an onion and I decrypt it, but it's I receive an onion, stash it away, and then look at it later once we have exchanged commitment signatures. So we add a lot of noise, but I do agree there is some signal left in there. Okay, and this brings us to basically Sphinx, the construction we actually use. And what we have here is the filler construction, which is really the only hard part in all of this, because it's weird how we use subparts of the stream to encrypt parts of the onion that are trailers. And I'm not sure you can see that, but I have sort of a shadowed out version of the clear text payloads here. And what we do is basically when the sender initially when it wants to create this this structure here, it will basically take this onion prefix here. It will add the filler or trailer or whatever you want to call it, and it will then go and generate the shared secret that will be used to decrypt it, and it will encrypt this whole thing, throw away that part, and only keep this. Okay? So it will encrypt this part. Now, for the next hop, what we need to do is basically we need to take this part, shift it here, and add the filler that the second node would add. And now we again generate the entire encryption stream and encrypt this whole this part here and throw away the beginning. So we have one more layer of encryption. Yes.
Why exactly do you need to cover the filler for both with the HMAC? I don't see why it would matter if there's someone is tampering with the filler.
So by if you were not to cover the HMAC with the filler, the filler with the HMAC, then you would have to communicate to your peer which parts are covered by the HMACs. If you only were to cover this part by the HMAC, then you would need to tell A, who is going to receive this packet, hey, you are supposed to only check the first 4 of these, right? It's not actually only easier, but you're actually telling A that this route is only 4 hops long. And here you say B, hey, this route is only 3 hops long. And this guy, hey, it's only 2 hops long. And this guy, well, this guy knows he's the final one.
The general advice is to never encrypt anything without marking. It's always a bad idea. Because then you can manipulate tons of different stuff.
And the reason why we HMAC not only the payload destined for the processing node is exactly that, because then if A receives this packet here and only checks the HMAC here, then somebody before him could basically tamper with a C. And if then that HMAC fails, we know, okay, it's at least going to be B and C. So by tampering with individual parts of this onion, you could basically start probing, hey, how long is this onion actually? And you'd lose all of the security again that you just bought really expensively. So this whole filler construction is really the only hard part in this whole process, and it took me forever with paper and stuff to actually draw this out. So now we go ahead, shift that again. This is how the packet would be looking at the node C. We add the final filler, encrypt again the entirety, and then finally we get this last step, and we encrypt, and then we can start computing HMACs for all of these. And we compute them in reverse order, because this HMAC is going to be in the payload for E. This HMAC is going to be in the payload for D. And this HMAC is going to be in the payload for A. A, E, C, and there's one more, D, which I've left out for some reason. It gets really confusing because you have to reverse order a bunch of time. Okay. So the actual packet serialization we use in the update HLC format is we have a single version byte, which we recently found out we can never change. Sort of dumb, but we have an ephemeral key. Because if we change that, basically the entire network needs to switch that. No. It's not about the anonymity set, but if I give you version 1 onion, you decrypt it and you process it, we have not built a mechanism that we can tell you, hey, by the way, forward this as a version 2 to the next hop. So there is no, we can downgrade from version 2 to 1 by saying, by the way, in the payload, the next hop doesn't understand version 2. Please downgrade, but we cannot upgrade. Is kind of the whole point of this. Okay, I mentioned before that we have that we are performing ECDH to actually get the shared secret, and the ephemeral key here is the one that we are actually using to perform ECDH with the node's public key, with the node's private key, and this ephemeral key is basically a public key matching some private key that we randomly generated as senders. So when receiving, actually I have that on the next slide. Okay, so ephemeral key for shared secret generation, hop payloads, that's basically the 1,300 byte blob that we were just constructing, and the HMAC that is destined for, that is needed to verify before decrypting the hop payload. All good so far? Cool. And now for the pièce de résistance. This is the actual process of unwrapping and wrapping the onion. I'll start with the unwrapping because that's easier. So upon receiving a packet, we will use the ephemeral key and our own private key matching our node ID to generate a shared secret. Using that shared secret, we can compute an HMAC on the encrypted blob and compare it with the HMAC that we were given in clear text by the previous hop. Then we can append the filler, that is basically the zero padding at the end. We decrypt using the shared secret, and we use a ChaCha20 stream for that. We extract the hop payload. The hop payload is basically just once we have decrypted, the first 65 bytes contain the HMAC for the next hop, contain who is actually going to be the next hop, the CLTV delta, and the amount that we'd like to have the processing node forward. Remember, this is the sender talking to one of the intermediate hops, right? So the sender tells the intermediate hop, hey, you should forward to this hop with this CLTV delta, and that amount should then get transferred to it. And then we just take all of this information and serialize it again. So we take the version byte, we take the ephemeral key which by now has been tweaked using the shared secret. I'm actually missing that part in the slide. The ephemeral key gets modified by tweaking, by multiplying with the shared secret. This makes sure that that also the ephemeral key changes from hop to hop. So you can't look at two onions and say, okay, this is a precursor to this one, or this has anything to do with the other one, because the entire packet basically changes. We serialize that and basically propose an update add HTLC to the next hop, or we have some error because, well, we don't have the channel we were supposed to use wasn't active or something like that. So that's the unwrapping of the onion. This is pretty straightforward because it just goes one direction. Wrapping the onion is a bit more involved because it goes backwards and then forwards again. So we generate a random ephemeral key, and and using that we compute the shared secrets in forwards order. So that way we basically compute the first shared secret with the first node ID, and then use that shared secret to then generate, then tweak the ephemeral key for the next hop, and using that we then generate with the node ID and the ephemeral key we generate the shared secret and then tweak it again. And basically this is a forward process. Then we serialize the last hop payload, and just and since we don't have a next hop, the HMAC is going to be all zeros. And then in reverse order of the onion, because we are wrapping the onion, we write pad to 1365 0 bytes. This is to get the constant size. We derive the ChaCha20 stream from the shared secret. This is what we are going to use to encrypt. By the way, the encryption scheme and decryption scheme is XOR, so they are symmetric, which makes this whole thing a lot easier. We encrypt the onion, we compute the HMAC, put the HMAC inside of the payload, then serialize the payload inside, and we right shift this whole thing once, making room for the previous payload, which is the one we are currently processing. We serialize the payload inside of this 65 bytes of thing, and then we rinse and repeat. Well, right padding is not really needed. We basically chop off the end to make it to the size that we expect it to be. Derive ChaCha and encrypt and compute HMAC, add HMAC to the prior hop, and so on and so forth. And we do that 20 times or however many hops we have in here. And finally, we then serialize the onion and can use it when using update add HTLC. So the whole complexity here is that we generate shared secrets forwards and wrap the onion backwards. That's basically it. This is all done by the sender, yes. This is also why I'm saying that actually computing a route and then creating an onion packet is quite expensive. Also, implementing this is hell. It's funny is actually that the first code that I touched on C Lightning, and I was learning C and this stuff at the same time, I think I still haven't recovered. Anyway, so all that's left is basically add a few more details about what encryption we use and what HMAC and what shared secret. So we use Cha-Cha-20 for the shared the encryption stream. The stream is initialized using a shared secret that we derive from ECDH. And from that ECDH process, we derive 3 keys. The row key is the encryption key, the mu key is the HMAC key, and the key is what we use for the error on the backwards route, which is a stupid joke I came up with because it's backwards mu. You've got to have fun sometimes. HMAC is SHA-256 because that's all Bitcoin knows. All Bitcoiners know. Okay, 2 more slides, then we're done. Returning an error. So this whole process is going forwards, right? This is a one-shot routing packet that we can only ever go forward. And the question is, if something goes wrong, how do we return an error? How do we tell the sender, hey, something is wrong here? And we don't have a good construction of how to create a backwards onion using just Sphinx, because we heavily modified Sphinx to not include a payload anymore for the final hop. And so what we ended up doing is we rely on pre-existing information, right? This onion does not exist in a vacuum. This onion is associated with an HCLC. We can store the shared secret with an HCLC. And so whenever we fail an HCLC, the previous hop can actually look at the shared secret, look at the key, and use that to encrypt whatever error we had. So that way we can rewrap an onion that contains an error. Now this onion is a bit simpler. It's a lot simpler actually, because there is no HMAC. We don't have a good way for any intermediate node that doesn't have any information about the path to create HMACs that could be verified by individual hops. It's also not constant size, because hopefully this happens not that often. But it will not change during the forwarding of the error. So if I have a 60-byte error message that I'm trying to get back to the sender, it will be 60 bytes all along. It will just be encrypted using the key at every hop. And when receiving the error packet, the sender can actually regenerate all of the shared secret, or it has stored them somewhere, and then can decrypt until it finds a valid error message, at which point it knows, okay, which node failed is returning this error. So yeah, this return onion is really simplistic on purpose, because we hope to eventually find something that is more stable, but still working on that. Recent developments. So far, I've told you about how this is actually implemented right now. I have like 3 pending PRs on the specification that all try to get us away from this fixed 65-byte frame. 65 bytes, by the way, was chosen because it's 64, which is a nice number every CS guy likes. Plus 1 byte, which is sort of the payload type, realm as we call it. So totally arbitrary. It was just the smallest power of 2 that would fit our payload. The initial proposal was basically to allow having multiple onions, multiple hops be 1 payload. So basically say, okay, we can decrypt, and the first byte or 2 bytes would tell us how many frames to use, and that would be our payload. And then we would also shift accordingly. So if we were to use 2 frames, each 65 bytes, then our filler at the end would need to be 130 bytes. And we would also need to encrypt that many more bytes. That worked, but it was still not flexible enough. So we came up with a different scheme where we basically, instead of having these fixed size frames, which we were using to enforce the 20 hop limit, are now completely gone. And the first 2 bytes basically tell us how many bytes our payload is. And that gives us the opportunity to actually pack our payloads much closer and to basically aggregate what we were using as padding inside of the payload and add additional hops at the end. Or basically add an arbitrary payload for any of the intermediate hops inside there. And if you were wondering, that's also how we could fit an onion inside of an onion. By basically having a 19-hop onion inside of a 20-hop onion, there's enough room for us to basically have this large piece of data inside of a slightly larger piece of data. And once we have that, we can do a lot of fun stuff. So one of the proposals that we were talking about before is having the AMP proposal, which requires us to put a bit more information there. Basically, hey, you are about to receive 60 Satoshis. I know this is short 10 Satoshis. Please just wait. And by adding that information in there, we can tell the recipient, hey, you should be waiting for more. We can have stuff like spontaneous payments, which we just figured out lately that we don't actually need to put in the onion. So yay. And we can have stuff like rendezvous routing. So rendezvous routing basically is that the recipient tells us a part of the onion, and the sender basically prepends its own path to whoever the rendezvous or the meeting point in the middle was. I can say, I'm the recipient. I want you to communicate through Richard, and I will give James. I will give you an onion that leads from Richard to me, and you will not be able to see that I'm the final destination. All you will see that you're supposed to communicate through Richard, and so you will take that second half of the onion and prepend your path to Richard, and then we can communicate in this way without either of us knowing who the endpoints are. Well, we need out-of-band communication for that. And the reason why we need that, why we need bigger hop payloads for that, is because of the ephemeral key. We have no way of generating an ephemeral key such that they meet up perfectly at Richard. So what we need to do is have an ephemeral key inside of the onion, and then basically when Richard gets your onion, he will be instructed to prepend this switch out the ephemeral key with the one that was transported in the onion itself, and then this all works. But otherwise, it's kind of hard. I mean, it's actually cryptographically proven that you can't really meet up in the middle. Otherwise, you'd have broken some cryptographic assumption. I think that's most of the onion stuff.